For the last 3 years, we've been using artificial intelligence completely wrong. I mean, think about it. We've taken these massive, state-of-the-art large language models and basically treated them like, well, ultra-glorified text autocomplete machines. You type a prompt, it spits out a giant wall of text, and then who has to actually do the work? You do. You, the human engineer, are stuck manually copying, pasting, debugging, and actually executing the code. It's slow, it's painfully manual, and it completely misses the true potential of the tech we literally have sitting right at our fingertips.
So why did we get stuck in this rut? Well, we have to look at the interface we've all been obsessing over. That standard chat-based interface, it hit a massive, hard productivity ceiling. And the reason is simple. Answering a question just isn't the same thing as solving a problem. We essentially invented a supercomputer just to give ourselves carpal tunnel copying its answers. But listen, the tech industry hasn't just tweaked these models over the last few months. It has entirely shifted away from using them as mere conversational tools. We're officially entering the era of autonomous, agentic AI workflows. We're talking about leaving passive chatbots in the dust and moving to active agents. Agents that actually observe their environment, make decisions, call APIs, execute code, and self-correct until a goal is 100% complete.
The difference between these two paradigms is absolutely staggering. Look back at 2023. A passive chatbot hits an error, and what does it do? It either totally gives up, or worse, it hallucinates some fake answer. It has zero capability to interact with the system to actually fix the underlying issue. But fast forward to our new reality, agentic workflows. Here, autonomous agents actively solve problems by running code until the job is done. So in this explainer, we're skipping all the high-level fluff. We're diving straight into the hardcore engineering mechanics of how this actually works. Grab your coffee, spin up your IDE, and let's break down this architecture.
Section 1. How AI agents think. Unlearning the continuous brain.
Okay, to truly understand an agent, you first have to unlearn a really common misconception. An LLM is not a continuous brain. It just isn't. It's a stateless prediction engine. It takes tokens in, it spits tokens out. Full stop. So how exactly does a stateless text predictor take autonomous action in the real world? The secret sauce is the REACT framework, which stands for reasoning and acting. Instead of just immediately blurting out a final text response to the user, the agent enters a very specific loop. First, a thought. It plans out what needs to happen. Then, an action. It actually triggers a tool. Next, an observation. It looks at whatever that tool returned. And finally, reflection. It evaluates, hey, did this action move me closer to the goal? That core loop is the engine that allows agents to take real-world actions instead of just chatting with you. And here is the exact low-level magic happening under the hood. When you call an LLM API and give it tool access, you pass it a JSON schema that defines your function signatures. When the model decides, okay, I need external data to solve this, it completely stops outputting natural language. Instead, it emits special tokens structured perfectly as a strict JSON tool payload that matches your schema. It literally shifts gears from generating conversation to generating a highly specific API payload.
Let's actually look at this execution loop in real time. Because remember, the model itself isn't executing the code. Look at this timeline. Right at t0, the JSON payload is emitted by the model. Then, at t plus 10 milliseconds, the runtime environment wrapped around the model captures that payload and validates it. By t plus 50, it actually executes the function. Let's say it's querying a database. And finally, by t plus 100, it takes that raw return data and feeds it straight back into the model's context window as a role message. The agent observes this brand new data and just continues its loop.
Now, what is super interesting here is how wildly this contrasts with traditional software engineering. Normally, control flow is hard-coded by us, the developers, using rigid if-else blocks. But in agentic software, control flow is probabilistically generated by the model based on those runtime observations. Think about what happens when an agent hits an error. It doesn't just crash. It doesn't throw its hands up. It observes the error from the environment, reflects on that state change, treats the error as raw data, and dynamically chooses a follow-up tool to self-correct. It just keeps looping until it succeeds.
Section 2. The M-to-N integration nightmare.
Now, building this in the real world sounds awesome, right? But the second you try to connect a dozen databases to these workflows, you hit a massive wall. Let's talk about the dark side of agentic systems. 50. That's the number of custom integrations you would have had to write in the pre-standardization era if you just wanted to connect 5 different AI apps to 10 different data sources. Every single engineering team was out there writing custom wrapper code for PostgreSQL, custom code for GitHub, custom code for local files. You get the idea. And the worst part? If an API schema changed anywhere down the line, every single integration shattered. Total nightmare.
Honestly, it was exactly like the Wild West of web hardware before USB was invented. The industry desperately needed an open, unified standard.
Enter MCP, the Model Context Protocol. MCP is an open standard that completely vaporizes that custom integration bottleneck we just talked about. Think of it quite literally as USB for AI agents. It provides a unified client-host-server architecture built right on top of standard JSON RPC 2.0. This means developers can finally stop writing those endless custom wrappers and start plugging AI agents directly into the real world.
Let's look at how incredibly clean this architecture actually is. The AI host, which, could be your IDE or a dedicated agent runtime, acts as the container. It spawns these really lightweight MCP clients, and those clients maintain stateful one-to-one connections with standalone MCP servers using either standard input/output or WebSockets. Because it leverages these standards so cleanly, an agent can instantly connect to any local tool or remote server, run a quick handshake, and just auto-discover every single capability in real time. It's brilliant. So stripping away all the marketing hype, here are the exact JSON RPC API specifications engineers are actually using. An MCP server exposes 3 standard capabilities. First, tools. These are your executable functions the agent can trigger, like running a terminal command. Second, resources. These are read-only contextual data streams, like pulling live database logs or reading files. And third, prompts, which are basically pre-engineered templates to steer complex reasoning. If you want your AI agent to query production logs, you don't write a custom integration anymore. You just plug in an MCP server. Boom! Secure, standardized, plug-and-play access to any system.
Section 3. Engineering Safety Guardrails in Production.
Of course, giving AI agents plug-and-play access to the real world forces us to ask a rather terrifying question. What happens when an agent goes completely haywire? Let me be real with you for a second. Agents are not magic. In a production environment, they can break in ways that will keep you up at night. First up is runaway execution. Let's say a tool returns an unexpected error format. An agent can get trapped in a non-deterministic infinite loop. It might retry the exact same broken tool call 50 times in 30 seconds. This completely nukes your context window and will absolutely give your cloud billing department a heart attack. Then you've got context rot. As the agent's context fills up with thousands of lines of raw logs and outputs, the LLM starts suffering from lost-in-the-middle positional bias. It literally forgets its original instructions, gets super confused, and starts acting with high confidence on completely stale data.
So how do senior back-end engineers actually fix this? Spoiler alert. The answer is not just throwing another LLM at the problem to babysit the first LLM. Instead, we borrow proven, battle-tested patterns from distributed systems. The specific solutions we rely on are circuit breakers and context compaction. This is how you actually team these agents and build resilient architectures.
Let's dive into the circuit breaker pattern. A circuit breaker tracks tool execution telemetry. If a specific tool fails, say 3 times in 60 seconds, the breaker trips into an open state. What that does is instantly block the agent from making any further calls to that failing service. So instead of letting the agent loop endlessly and burn through thousands of dollars, the system throws an immediate exception back to the agent. This forces the agent to stop, reflect, and pick an entirely different strategy to solve the problem.
And for truly high-risk operations, we're talking modifying production databases or pushing code commits, we implement right-gated, human-in-the-loop guardrails. Rather than stopping the agent at every little step, structural policy engines step in. They intercept the high-risk tool call, pause the agent's state completely, and ping a human developer with the exact parameters the agent is trying to execute. It then waits for cryptographic approval before letting it proceed. These are the mandatory, strict guardrails that transform a fun, experimental demo into reliable, enterprise-grade software.
Section 4. The Autonomous Future.
We are witnessing a fundamental paradigm shift in technology right now. The era of typing a prompt into a simple chatbot text field and just praying for a good code snippet is dead. I want to leave you with this crucial thought. Your job as an engineer, or frankly, as a knowledge worker in any field, isn't being replaced by AI. It is evolving. It's evolving from writing raw syntax to orchestrating these massive autonomous workflows. The tools are here. The protocols like MCP are standardized. The architecture is fully laid out. So here's the ultimate question you have to ask yourself. Will you be the one writing the raw code or the one orchestrating the agents that write it?
Thanks for joining me on this explainer. I hope this deep dive gave you the structural understanding you need to start actually experimenting with agentic workflows. Keep learning, keep building, and I will see you in the next breakdown.